Hello. So we are live. Welcome everybody to the Together webinar. This one is interesting. I'm really excited about this one. So Maurice is joining us, and we're going to be talking about pre-training and very large data sets. We released a RedPajama dataset paper recently. It was presented at NeurIPS. So Maurice is going to give us about a presentation that goes into the data set and how pre-training for these language models works. And then we'd love to take questions from the audience as well as you guys tune in. So feel free to throw those in the LinkedIn or the YouTube video chat, and we can see them on our screen over here. Reese, ready to go?
Yeah, thanks,
Awesome.
thanks, Lane, for the nice intro. You can see my screen, right?
1 second. Let's just do this.
Perfect. Yeah, cool. So welcome everybody to this webinar on the RedPajama datasets. I'm Maurice, and yeah, I'm gonna walk you through the webinar. So yeah, so if you wanna ask questions, as Zain said, you can just do live questions, and I'll try to answer them to monitor the chat a bit. And yeah, so let's get started now. So the RedPajama datasets, right? We released them in, I think, around March 2023, the first one, and then October 2023, the second one. And since then, these datasets, they've been adopted and used to train LLMs. So that's why we wanna give this webinar on and kind of provide more details and show how we built the datasets, why we built them, and so on. And yeah, so maybe to start off, let me introduce myself first. I'm Maurice. Yeah, I'm a researcher at Together AI, and I work mostly on modeling and data. So that means create data sets for model training. We also work on models, developing models, kind of changing models, etc. And yeah, before joining Together, I did my PhD at ETH in Zurich, and I've also led the development of the RedPajama datasets. And yeah, I'm passionate about AI. I like building large data sets, large scale data processing pipelines, and of course also open source and finally also I like making models, making LLMs faster. So that's a few words about me. And let me quickly tell something about what we're going to talk about today. So we start with a brief introduction to LLM training. So I want to bring everyone on the same page on kind of what steps or what components are in an LLM training pipeline from start to finish. And then I'll walk through the RedPajama journey. So showing a bit kind of where we started, where we went to, and then yeah, introducing the two data sets, the RedPajama V1 and V2 data set. So providing more details around them, and then finally I'll show a hands-on kind of notebook on how you can filter the RedPajama data set with a relatively simple example. And yeah, then we have also some time for Q&A. So let's start with the introduction to LLM training. So an LLM training pipeline consists of several stages. So on the one hand, we have the data collection stage, right? So we need data to train LLMs, and this includes collecting data from the web, from code repositories, science papers, etc. And this can be really large amounts of data. So it can be up to petabyte scale. So for example, the Common Crawl archive is multiple petabytes, I think. And then, what you need to process this data, you need compute for that, and it's typically CPU clusters. It's possible to do some steps be accelerated by GPUs. So, for example, if you want to annotate documents with different LLMs, for example, so like small LLMs that give you quality score for a document, then you need GPUs to accelerate it. But typically, it's large CPU clusters that are used for data prep jobs. And then in the second phase, it's the most expensive phase. It's the pre-training phase. And here, we have a lot of data that we've sourced in the first kind of stage. It's curated data. It's typically of lower quality than the post-training steps, but it's high quantity. So it's really a lot of data in the terabyte scale, in the trillions of tokens, and yeah, so it's a lot of data that you use for pre-training, and the models are trained on large GPU clusters, so typically thousands of GPUs, depending on model size, of course. And it also takes longer. It takes months of training rather than days, as in the post-training steps. And here during post-training, you have your pre-trained model, and then you kind of want to get the kind of increase the skills that the model has. And here you have more high quality data, lower quantity, and you often also have a human in the loop. So humans that create data, basically, right? So there are companies that have a pool of human annotators. They have like they have contacts to like PhD students, for example, and these PhD students they create data, they annotate data, make samples, things like that, and then also synthetic data, of course. And the training here happens on smaller GPU clusters, so typically on dozens of GPUs rather than thousands, and it's also faster. It takes a few days for training. And similarly in the reinforcement learning stage, so this is not always done, but sometimes. And here you also have like high quality, low quantity data and both of them rather in the gigabyte scale rather than terabyte. Yeah, so this is kind of the whole pipeline, and where we have to situate RedPajama is in the first two, basically. So RedPajama is not a post-training data set, it's a pre-training data set. So that means, yeah, it's lower quality, but high quantity. So that's where RedPajama is situated. And to give a concrete example quickly what even is LLM training data, right? It's text primarily. And this text, it gets tokenized. So when we say we have 100 trillion tokens, then what we mean is really we have 100 trillion of those kind of subwords words, which are represented as tokens, and they get encoded as integers, which can be read by computers, basically. So that's kind of what a token is. So if you imagine 100 trillion tokens, that's 100 trillion of those individual kind of subwords, or commas, words, parts of words, etc. So that's what a token is, and that's how pre-training data roughly looks like. So with that, we can now move on to the RedPajama journey, basically. And yeah, so to kind of put it a bit in perspective, right, to show kind of the history a bit. So before we released the RedPajama datasets, there were a couple of pre-training datasets as well. So for example, C4 or the Pile, which were really amazing datasets. They were very influential, or they are very influential in pre-training data. And around February 2023, Meta released the Llama 1 tech report and model. And the really exciting thing about it was that they showed that you can train state-of-the-art language models on just public open data. So that was kind of the spark for the RedPajama datasets, because in their tech report, they provided a kind of a description of the dataset, but they didn't provide the dataset itself. And so we decided we should try to replicate that and train models on it to be fully transparent from start to finish, have a fully open source model. Open source meaning both data and open model weights, basically. And then we built this RedPajama v1 dataset, and there was a follow-up dataset, SlimPajama, released by Cerebras, also a few months later than RedPajama, and they took RedPajama and deduplicated it. They added more deduplication filters and also kind of removed very short documents and things like that. And there were also, I also want to highlight the Dolma dataset, which is also a really amazing dataset, released by LNAI, which is also a compound dataset with multiple sources. And then in October, we wanted to make a bigger data set, and we built RedPajama v2 October 2023, and this was at the time the largest data set, so it's the one that contains 100 trillion tokens, and it was only web data, so only based on web data. And then there were more also really great data sets, so the fine web data set and DCLM baseline data set, and then the most recent, I think, is the TXT 360 data set, which was also released recently. So we see that over time, those data sets, they got much bigger and better, and kind of all those, they're all open data sets, right? And in the same time, also the gap between open weight models and proprietary models kind of narrowed over the last 2 years, more or less. Now, it's probably not just because of open data, but my guess is that there's also open data also played its role in that. So we see kind of this whole ecosystem of open models and open data kind of close this gap to closed source or proprietary LLMs. And there's also on RedPajama, there were also some models trained on it. And as I mentioned, this RedPajama dataset was built from RedPajama v1. So for example, Snowflake Arctic was trained on RedPajama v2. They took the quality signals and filtered it down to a better dataset, which was exactly what the RedPajama v2 dataset was intended to be used for, how it was intended to be used for. And then there's also more models that were trained, at least on parts of RedPajama, or at least part of the data set was sourced from RedPajama. Okay, so this is kind of the story around RedPajama, the journey around RedPajama. And now let me dive a bit deeper into the data set itself. So as I said, RedPajama v1 the goal was to build an open and best effort reproduction of the llama training data. So that was the primary goal that we tried to do. And we literally, when the report came out, when the Llama 1 report came out, they had this one page of description of training data, and we took this page and tried to turn it into a data set, basically. You can see it like this, and this was kind of the spark for it, and this resulted in a corpus that consists of 7 sources. They're primarily English. And the 7 sources, they are common crawl, so web text. You see them here: common crawl, Z4, code. We also have Wikipedia, books, etc. So it covers a few domains, a few different sources of data. And we reproduce those filtering steps and those deduplication heuristics that were shown in the report. And overall, the data set contains roughly 1.2 trillion tokens, which is also roughly for how many tokens the Llama 1 model was trained on, the Llama 1 models. Now, what I want to highlight here, which is important, is that we believe there are still gaps to the actual original Llama training data. That's because we did not have all the details. So the report, it was a one-page description of the data set, so we couldn't, exactly reproduce it. We believe, but we believe it's relatively close. But there are gaps, and we had to make some decisions basically on how to, on filling these details. So for example, we didn't know which common crawl snapshot was used, or we didn't know what kind of classifier exactly was used, how it was constructed. They do have some details on it, but not enough to exactly reconstruct it. And then also the GitHub filtering rules. So we didn't know exactly which exact rules were used. So we had to make a lot of guesses, and this inevitably leads to some inconsistency to the original Llama training data. But it's kind of best effort guesses. So, and to kind of validate this data set, we wanted to see how far away or how close are we to the actual Llama training data. And we validated this by training LLMs on the training data and on that pre-training corpus, and then see how close do we get to the performance. right? Evaluating it on benchmarks. And we pre-trained models at 3B and 7B parameter scale, fully open models. They were trained on the supercomputer, on the Summit supercomputer at Oak Ridge National Lab. And this supercomputer, there's a few things to say here. On the one hand, it's V100 nodes, so it's not A100 or H100 nodes. And they only support FP16 precision, so that means we cannot use mixed precision. And also we had to use lower learning rates than were used in the actual Llama paper. So this is kind of one source of inconsistency, and the other is the data set, as I mentioned earlier. And then, so then we evaluated the models once we trained them. The 3B models, they performed quite well. So they outperformed, for example, PyTia 2.8b. At the time, these were among the state-of-the-art models, which was in summer 2023. And the really interesting part is also that the 7B base model, it was slightly behind the Llama 7B model on Helm. And now we believe this is exactly due to those inconsistencies that we had when constructing the data set on the one hand. And the other part is probably also kind of the different hardware setup. So lower learning rate, loss scaling, and no mixed precision. So so that was kind of, those are two sources which we believe led to this. But other than that, it's relatively close to Llama 7B and also to Falcon 7B. So this is about the RedPajama v1 data set so far. Do we have any questions so far? I think not yet. If I'm not, are we going to get the slides? Yes, we can give them. All right. Oh yeah, okay. As he's saying, already answered here. That's great. Good. Okay. Now let me move on to the RedPajama v2 data set. So as I said, we wanted to scale it up basically. So we wanted to create a bigger data set. And we made that decision, I think around summer 2023. So this illustrates it. So basically this was, the small Llama was RedPajama v1 and the other one was RedPajama v2. So we scaled it up. And we did that by taking web-only data. So we processed the largest part of Common Crawl. We kept 5 languages. I'm going to go into more details in a bit. So the Common Crawl web corpus, it's really big. So Common Crawl is an organization that regularly scrapes the internet for web data, for text data, I should say. I think in every 2 months or every 1 month, more or less, since I think it started in around 2010, 2009. And they do this and kind of release this data in HTML and in text format. And this is really a big resource. Most of the open web data sets, they're built on Common Crawl. And the RedPajama v2 dataset, is built from that, and we have so it's relatively raw data, and we enrich it with quality signals to filter it. So to put it in a few words, basically what RedPajama v2 is it's a web-only data set that consists of 5 languages, 120 trillion tokens, and it has quality signals to filter it, basically. So that's what RedPajama v2 is, and how we built it. As I said, we took Common Crawl and processed 84 Common Crawl dumps from it. A dump is basically one crawl that was created during 1 month. And the data ranges from 2014 to 2023. And there's one important detail to mention here. So we took the .wet files, and .wet stands for web extracted text. And this is the text which was already extracted from HTML code by Common Crawl. So there's two, so basically for each crawl, for each dump, there's 2 different kinds of data. One is just the raw HTML code, and one is the text extracted from the HTML code. Newer data sets, they directly took the HTML code and parsed it themselves, because parsing HTML is quite intricate, and yeah, it's hard to get right, I think. But it's a it's a manageable size, and we took the .wet files. I think originally, yeah, it was the data, the 84 common crawl dumps was close to 1 petabyte, I think. And we then processed it with CCNet, with the CCNet pipeline. And this CCNet pipeline is it's released by Meta. They released it to process data, and it's very kind of lightweight processing. And what it does is, and this is exactly what we wanted to have, basically. So we wanted to not make a lot of assumption on how to process the data. So we wanted to have something lightweight. And what it does is it deduplicates paragraphs in shards. So basically it takes a few 100,000 documents or so, puts them into a bucket, and then within that bucket, it deduplicates the paragraphs. So individual lines, basically. You can imagine it like this. And within that, within that bucket of those 5K, 10K, whatever documents, you have unique paragraphs, basically. And since it's billions of documents, that there are still duplicates around, but within buckets, there's some level of deduplication there. And this is just one way of deduplicating, a relatively light way of deduplicating. And then the other part the CCNet pipeline does is identifying the language. So it has a language filter with a fast text model. They are very popular and fast models to identify the language of a piece of text. And we kept the 5 languages. So we kept English, Spanish, French, German, and Italian. And then the other part that the CCNet pipeline does is an annotation step, which is the Wikipedia perplexity. And what that is, Wikipedia perplexity is basically, so perplexity is a score. It's a numerical score that tells you how perplexed, in a way, a model is when it sees a new piece of text. And that model is also a small and very fast model that was trained on Wikipedia. So it has only seen Wikipedia text. And the score tells you how surprised, in a way, this model is from seeing a new document. And kind of the hypothesis here, or kind of the assumption here, is that Wikipedia is a relatively high quality source. And if this score is high, then this new document is a lot different from Wikipedia, basically. Now we didn't filter with respect to Wikipedia perplexity or something like that, but we just kept the score, so that we can filter based on that score. And this gives you so the Wikipedia perplexity gives you 3 buckets, text documents with low perplexity, middle perplexity, and high perplexity. We categorized it into these 3 buckets, but we didn't remove anything or so based on that, because we think it's not the only way to filter web data, and that's very important. Okay. In RedPajama v1, actually, we also used this pipeline, and there we kept only the kind of the top 60%, I think it was. So the best 60% of data. And yeah, so this led to the RedPajama v2 data set, kind of the raw text. English is the most parts of it. It's just in the internet you have so much English, and not as much Spanish, French, German, and Italian. But still, it's big corpus. It's 10 trillion tokens Spanish, French, German roughly, and 5 trillion roughly Italian. I see there's a question. Is this language choice? I think I can click on it. Okay, or not? Oh, no. So let me read it quickly. So is this language choice related? The question is this language choice related with the importance of these languages at a European level? Why not Portuguese? So the choice was, in principle, we could have any language, right? But we made it manageable, and these were kind of the biggest languages that we had in Europe, basically. But yeah, I mean, in principle, there could be that. There's no reason why not Portuguese, basically. another question: are data collection and processing scripts available to check them out? Yes, they're available. We can link to it later. It's the GitHub repo is called RedPajama Data. RedPajama Data. Yeah. We can link to it later. But yeah, they're available. Oh yeah, perfect. Thanks, Zane. Yeah. Okay. I think that's all in terms of question. Yeah. All right. Yeah. So this is, as I said, this is the raw text, and this is kind of, still relatively noisy text and noisy. There's a lot of bad quality, low quality samples here as well. And this is intentional. So we wanted to keep the low quality text, and this low quality text can be, it can be multiple reasons why it's low quality. It can be due to parsing errors. So the HTML parser is not perfect. I don't think it exists a perfect HTML parsers. So there are errors for sure. There's also things like, a lot of repetitions, for example. So samples which are, for example, one page which has a lot of menus with click here, click here, click here. And then this is kind of text that is not very informative. It includes this, and we deliberately included it because we wanted to provide the community with tools and the source basically to figure out what is good data, what is bad data, right? So we don't fully know what is good data, what is bad data, right? So we decided to keep everything and just rather than filtering it ourselves, we decided to publish quality signals with it. And these quality signals, they measure how, or they're kind of an approximation to measure how good the document is, basically. And we went through the literature and kind of collected all these quality signals that were used to train different models. For example, the Gopher rules, the C4 rules, and also ML heuristics and others. And they can be roughly categorized into 5 categories, these quality signals, and they're a really important part of the data set. And so one category is just natural language. So that means, for example, how many words are there in a document. So very simple things. Another quality signal would be how many symbols. So non-alphanumerical characters are there in a document. How many bullet points. These are all indicators, or these can be used as indicators to how natural a given piece of text is. Then the other part, which is also important and which happens a lot in web text, is repetitiveness. And this is things like, how many characters of a document are there in the most frequent word. So if, for example, a document contains only 2 words, right? And this word is, or like 3 words or whatever, and most characters are just in 1 word, then it's kind of, it's probably a bad quality text. And you want to filter this out. And these are the repetitiveness quality signals. And then there's also content filters. And this is, we call it content filters because it's basically, it tells you whether a website that was crawled by Common Crawl is banned by a list of banned URLs, basically. So the University of Toulouse releases this list. I think it's weekly, or I'm not sure, weekly or monthly. And they release this list of those blocked kind of URLs which contain like I don't know, violence or things like that. And we keep the data, but we provide a signal whether or not that document is banned, or the URL was banned, basically. And then there's also a list of dirty words, so like a bad language words, and things like that. And we also keep it as a quality signal. So these are content filters, and then there's ML heuristics. So one of them I already hinted at before. It's the Wikipedia perplexity, for example. Other things are language score or a model trained on. So there's also classifiers. So for example, a fast text classifier that was trained to distinguish between high quality and low quality text. And we have different choices of what is high quality and low quality, right? And we provide the scores of those classifiers that tell you how whether the classifier thinks it's a low quality or a high quality document. And then finally, there's also deduplication signals. So this tells you whether the document is duplicated or not globally. Yeah, okay. So these are basically all those quality signals, and they can be used to reproduce Gopher rules, C4 rules, and others. And this is what we're going to do now in a simple example. And they can also be used to create new filters, of course. So we don't need to stick to those rules, right? So yeah, now we have the hands-on part. Let me quickly connect here to the Jupyter notebook. Yeah, so we're also going to make this Jupyter notebook available later. And what we use to filter, so we have the data set, just a small fraction of it for the sake of illustration. And what we use to filter the data, kind of the library we use is Deft. It's a relatively new library, and it's really amazing. So I can recommend to everyone to check it out. It's super fast. It scales to hundreds of CPU nodes. And you can use it to read data from either from object storage or from local disk, and they have also connections to other kind of data stores. And it's relatively, so if you know pandas or polars, it's quite easy to adapt to Deft, and it scales much better than pandas or polars. So we use it a lot, and you can just install it. Let me run it with pip installable, and yeah, it uses Ray under the hood to scale to multiple nodes. All right, so it's already installed now. You import it, and now you can read data, so Parquet data with just def.read Parquet. Here I have the data file on disk, but yeah, you can also connect to an S3 bucket or R2 bucket or wherever your data sits. And you run it like this. So def.read Parquet, and you can count how many documents there are. So here we have 42K documents in that data frame or in that Parquet file. We can look at the data, how it looks like. So here you have different columns. So the text here is here, and then we have all the quality signals. They start here. So this is, for example, a repetitiveness quality signal. How many characters there are in the top 2 gram, for example, and then we have different ones, kind of how many lines and the fraction of lines in the document that end with an ellipsis. So ellipsis is the three points, and so on, right? So we have all those quality signals here and the text as well. What are the questions so far? Okay, nothing yet. Good. And one way of using the Deft library to filter the data is with SQL queries. So this is a really handy and kind of very intuitive way of filtering the data. And we're making 2 examples. So one is just filtering with respect to how many how many words there are. So we want to have at least 20 words here, for example. So RPS doc word count is how many words there are in a document, and the other is the fraction of uppercase letters. So this filter does not make sense probably, but just to illustrate the kind of what you can do and how you can run it. And so you can literally write in a string the SQL query. So you select text, and let's also select this one from the data frame. So you reference it with from df here, where this is true, right? So let's run this, and then we can execute the query with this syntax. So the interface is just def.sql, and it identifies. So we see here is no, there's no df here. Our data frame is called df, right? And def here just scans kind of the Python namespace and figures out that it has to use df as the table where to scan from. All right, and then those 40K are now only, how many are there? Let's see. Uppercase letter .count .show. There's not many, 5. That 5 of those 42K documents have at least 20 words and more than 70% uppercase letters. And we see now here in the text, there's a lot. This one is almost only uppercase letters. Here you also have a lot of uppercase letters and so on. So this is one way of filtering the data set in a simple example, but we can also do more, right? So we can create much more complicated queries. And the Gopher rules, so this in the second example, we use the Gopher rules. And they consist of, on the one hand, the quality filters, kind of heuristics that tell you whether a document is of high quality, low quality, and repetition removal filters. And yeah, it's a really good paper from, I think it's 2022, from Google DeepMind here. And they go into a lot of details on those rules, on those rules. And if we want to apply them, so I'm not going to go through each of the rules, but if you want to apply them, you can again write this SQL query just as a string. So let's call it Gopher pass query. And then here, what I wanted to do is I want to keep both. So I want to keep both documents that get filtered out and that get kept by the Gopher filter. So whenever it's true, then when it gets kept, when it's being kept, then we have 1, and otherwise we have 0. This is going to be a new column in the data frame. We can quickly run it. And now let me remove that quickly. And now we have a new column here, Gopher pass, right? So 1, 1, these are all being kept, and others are being rejected. We can quickly look at it. So these are all rejected. You see that here, right? It's 0. And then you can write it to disk, which is, if we want to keep everything, then we can write it like this, .where. That's the def syntax, but we can also keep everything, write it again to disk, and there you go. And now we can also quickly look at the data. So I've put it into Lilac. Lilac is a very nice library to visualize data, text data. So whenever you train models or whenever you do work with text data, you should look at the data basically. And Lilac is a good interface. So we can, you see here, this is one document, for example, probably doesn't contain a lot of, I don't know, information. And yeah, so these are now not filtered, but you can also then here select the filter, Gopher pass, and we see, if we set it to 0, meaning it has been rejected. And now we see this is probably, not sure why exactly, but probably a lot of kind of non-alphanumerical letters. Yeah, or different reasons, right? For maybe too short. A lot of ellipses here, for example. So yeah, that's what you can do with RPV2 and the def library to filter it. All right, so that's already it. I want to thank everyone for being here, and I also want to highlight that we're going to be at NeurIPS in Vancouver. So if anyone's there, come pass by our booth, and we have multiple posters as well and spotlight posters. So feel free to pass by if you're there. So with that, I would say, yeah, we can move on to Q&A time.
Awesome. Thanks, Maurice. We do have a question here in the chat. Let me put that up on the screen.
Yeah. Okay, what is the key application of this framework? Can we train any vertical domain models with it? Does your platform? So it's not, so if you mean framework, if you mean the depth library, this is just a library to filter data and create new data sets. If you mean the data set, yeah, you can in principle filter out new domains from the data set. But it's not a, it's not a platform itself. So we also have not together we have not productionized this, right? So it's a data set that you can download from Hugging Face, and then then you can create new data sets from it and train your models on it.
Yeah, this is similar to a question that I had actually, which is you mentioned that there's different languages within RedPajama. Are there also different like subdomains? Like maybe there's a math section of the data, entertainment section of the data. Like, do we have those subcategorizations already done that people can filter on, or do they have to build those in themselves?
Oh yeah, that's a great question. We don't have them annotated like individual subdomains. You can probably take the domain names kind of as a proxy to that, or you can have a domain classifier. So for example, NVIDIA released domain classifiers recently, a few months ago, I think, and yeah, you can basically use those and run it over the data set. But we ourselves have not done it yet. So it's
Okay.
yeah, we don't have that, but you can do it, of course.
Okay. There's also another question here. Let's take this one.
All right. Can you share some metrics on the time CPU hours engineers required to process these kinds of data sets? Yeah, of course. So the RedPajama V1 data set, we did this as a team of, I think, so purely the data processing, we were around 8 to 10 people, I think, and each of us worked on a different slice. In terms of CPU hours, I don't have it on top of my head, but I can tell you maybe how many nodes we used, and we used around 12 nodes in total, and we used them for, I think it was around 10 days or so. So that's kind of the more or less the order of magnitude we used for, and there were a lot of trial and error as well. So you write code, it fails, and then you do it again. But yeah, more or less that timeline. And then RedPajama V2, it was mostly me who processed it, and C as well. And we used 16 nodes there for around 1 month or so, 1.5 months, I think it was. Yeah, and we wrote the code. It was bare metal machines. Yeah, and each machine had 64 CPUs, 500 gigabytes of RAM, and yeah, we used those 16 machines for processing it.
Yeah,
Thanks for the question.
Yeah, that was a great question. This is something that I was thinking about last night as well, where a lot of people talk about compute required for training and inference, and nobody ever talks about the compute required for data processing and getting like this data diet that the model is going to eat ready, right?
Yeah.
So maybe one follow-up question on that. Why do we need CPUs for data processing, but GPUs for model training and model inference? Can you differentiate the
Yeah. So yeah, that's a good question. So for data processing, it's typically like string operations and simple string operations that you do, and the kind of computation is not big matrix multiplications, and this is not so. Yeah, it's not as easy to accelerate, I think, with GPUs. The text processing, basically, kind of this very basic text processing. Whereas in training models, you need the GPUs for the matrix multiplications, basically. So that's a big difference. There's ways to do, for example, deduplication with GPUs, accelerated by GPUs. So NVIDIA, they have this really amazing library called NeMo Data Curator. They use GPUs to accelerate deduplication, so to compute hashes and to run near deduplication, basically. And also, if you wanna, if you have a small model, so for example, Hugging Face released those small LM models, and you can use those to scale them up to hundreds of or to trillions of tokens and annotate them with small models and prompt them to say, is this a good document or a bad document? Does it contain a lot of information? Is it information dense or not? And things like that.
Yeah, this is interesting. This is another thing that I was thinking about. Why do we need both heuristic filtering, but then also model-based filtering? Um, wouldn't model-based filtering just be able to handle all of the heuristics, or is it just computationally efficient? Why does the pipeline have both?
Yeah, that's a great question. I think it's mostly the heuristics. They're just much more cheaper to run. So those rule-based heuristics. And what you typically do is you first have, you have your raw data, and then you apply kind of the cheap processing. So meaning you throw out all documents, for example, which are really short, like only 5 words. And this can be done, you would do that first, and then you would take models to annotate or to classify, like more expensive models once the data the data set is smaller. And it's, yeah, as you say, it's because of cost, basically.
Okay. We also have a good question in the private chat here. They say, if we only pre-trained a language model on text with uppercase letters, just as a hypothetical, will the language model only be able to reply in uppercase letters?
Yeah, I think so, because it is trained on. If it's only trained on uppercase letters, it has only ever predicted uppercase letter words from whatever its context is, right? So it's trained on next token prediction, right? So it has like the context, a few words, and then the next word, and it needs to predict this next word. And if it only knows uppercase letter, it will only generate uppercase letter, highly likely.
Yeah.
Yeah.
Another question here. They're saying they might have missed this, but what's the storage format for the final RedPajama dataset, and what impact does that have on training performance?
Oh yeah, that's a good question. So final RedPajama dataset is just text, right? So the way which we provide the data is in text format. It's JSON-L, gzip compressed JSON-L data, and yeah, it's text. And if you train a model, then you will tokenize it, and I don't know, you store it, for example, as NumPy arrays or whatever your training pipeline, whatever format your training pipeline needs. But it doesn't. I think it does not impact. So I mean, it impacts training performance probably to some extent, but how the actual, how the tokens are stored basically, but the actual training data set, like the text itself, that doesn't affect the training performance, except if you do like on the fly tokenization and things like that. But it really depends on how you use it, I think.
Yeah. Awesome. Another question I had was around. Oh wait, let's take a question from the chat actually. They're saying, I don't know if the machine learning based quality filtering also includes LLM based quality filters, but would it make sense to train an LLM to distinguish high from low quality documents and so on, maybe even assign a score?
Yeah, good question. Yeah, so we don't include LLM based quality filters, quality signals, but the ones we included are fast text models basically, and these are cheap, right? You can train an LLM to do that. I think the FineWeb EDU dataset, they did exactly that. They trained an LLM, a small one, to distinguish, I think, high educational value from low educational value, and outputted a score basically for exactly what you're saying. Yeah.
Awesome. Um, there's another question about some compute resources. So maybe I can take two of these questions and turn them into one. So one person is asking about how training a language model on their GPU will affect its hardware lifespan. And then another person is asking about whether they can fine tune language models on low CPU resources.
So the first question, whether it affects. Okay. Trying to. No, this is not a question, right? This one that pops up here.
Oh, this one, yeah, that's on the screen here.
Okay. So the first one, whether it affects lifespan of hardware, I think that has nothing to do with the data, right? So that's just how long you use it basically, whether you train many models on it at some point. Yeah, data
Mhm.
the GPU will, I guess, break down or you have to repair it. But yeah, it's not really related to data, I think. And can you repeat the second question? Whether
Yeah,
you can train on CPU, right? I
yeah.
think.
So this one
Uh,
that we have on the screen.
I think potentially, if it's a really, I mean, it's going to be really slow. But potentially, if you quantize it a lot and do LoRa, for example, then maybe. But I, to be honest, I don't completely know. I guess to some extent you could, but typically you do it on GPUs. So I've never tried it on CPU.
Yeah, I do know that. So for this person that's interested, there is a company called, I believe, Neural Magic. They're looking at CPU level inference and CPU based
Hmm.
fine tuning. So you might want to look into what they're working on, but I haven't heard too much around CPU based fine tuning or inference either.
Hmm.
Um, okay, I have a couple more questions that I was interested in as well. So you can you so if imagine we're not using a crawler, we're just going from website to website. If you happen on a website, what does a good website for language model training look like to you? And then what does a bad one look like to you?
Yeah, that's a good question. So that's basically what is a good quality sample and what is a low quality
Yeah.
sample, right? Um, so I think so. There's different ways of saying, do we want to keep it or do we want to keep it not, right?
Yeah.
One thing is for sure, how much information does that document contain, right? Is it like just things like click here, then do that?
Mhm.
You probably don't need a lot of these, right? It's still valid language, but it doesn't contain a lot of information, right? For example, the Wikipedia article contains a lot of information, so you would want to keep it. Also, clean language, right? This is also something you want to keep. If it's very kind of grammatically incorrect, or maybe not just grammatically, but kind of just damaged text, basically damaged in the sense that there's a lot of errors, kind of not really natural language, yeah, things like that, then you would probably not want to keep it. That would be a bad quality example. Or if it's like really short, but you still need diversity in the end. You need to have broad coverage of of topics and of things that are on the internet, basically, right? It's also a question of, do we want a model to know what is cursing, right? It's kind of,
Yeah.
in some sense it should know it so that it doesn't curse, or maybe you want it to curse. It's not really clear, right? You can say, we keep it, but we mark it as do not do that during training, right? Like a conditional
Mhm.
kind of training. um, yeah, yeah, so these are very interesting questions.
And then I guess a follow-up to that, let's say we have a good understanding of what is good data and what is bad data. Um, I've heard a lot about how data quality can affect scaling laws, and it's not always just the more data you train on, the better it will get. How much? So let me put two scenarios. One scenario, I've got all the data in the world, but I've got limited compute, and so in this case, I'm training on equally as much on good data as much as I am on bad data. Should I go with
Hmm.
this scenario, or like here, I've got a limited budget, so I want to really curate the pre-training data and then tune on that. Which training dynamics will have better scaling laws in this case?
I think the latter one. So you want to have good quality data and diverse data, right? The trick is that you need to filter in the right way such that you keep the diversity. So just high quality, very good language does not yet imply that you have also broad diversity, right? And in terms of scaling laws, I think you can you converge faster if you have more high quality or good data, right? But you still need the diversity, so it's very intricate. There's a paper called Beyond Neural Scaling Laws. Neural scaling laws. So they kind of go into that one. I think it's this one. Yeah. So it's good high quality and diverse data is kind of the key.
Okay, awesome. So there's a question from Brian in the chat here. Assuming this has happened already, how have other teams attempted to update or supplement RedPajama with new data?
We have not yet seen that. People who updated the actual data. I know people used it to filter. So Salesforce, for example, they trained their LLM on RedPajama v2, and they implemented I think mostly the Gopher rules, and filtered the data. But there's no new data added to it currently.
I guess maybe as a follow-up to that question, one thing that I was curious about is how does the data diet that a model eats during pre-training affect its downstream capability? So is it true that if I train a model more on code data, it will get better at reasoning? Or if I train a model more on entertainment data, it'll be a better language model for storytelling or for more creative tasks like this? Or does it all just average out at the end if you have enough variety of data?
I think it definitely affects. So you can have good models also trained on only web data, let's say, right? So I think the DCLM baseline model was trained only on web data. But as soon as you add more code data, let's say 20%, 30%, 25% code data, explicitly code data, right? Then you get better reasoning capabilities. I think code capabilities also get better, right? So you get what you trained it on in the end. So if you trained it on only, like the uppercase letter example from before is a very good example, right? If you only train it on uppercase letters, you will only get uppercase letters. And likewise, if you don't train on math data, your model won't be as good as it can as if it was trained on math, for example. There's of course in web data, web data is kind of, it's big, right? So it also contains math data. So you can't the abstraction of having only web data doesn't yet mean that there's no code data or no math data, right? So in web data, there's also code and math.
Yeah, this
but
is
to answer your question.
It's like the equivalent of you are what you eat, but for language models and pre-training data. Yeah, that's awesome.
Exactly. Yeah.
We also have some more questions. So maybe we'll take the last question here and then we'll end it off because we're at the hour. So this question is saying, if we're trying to create a project that involves making a user's 3D model and incorporating AI for voice chat to virtually replicate a human, what would be the best? Oh, this is a really complicated question.
What would be the best approach? Should we use system prompts, fine-tuning, or train an AI from scratch? So you need all the modalities, right? So you need 3D modalities. So you need image, you need speech, if you want to replicate a human. I guess you also want to fine-tune it such that it replicates that human, basically. So if you want to replicate a human, then you need the data from that human. So you need to, I don't know what you need, but yeah, you basically need you need to fine tune it. I think you don't necessarily need to train from scratch, right? Depending on, well, potentially you need to train from scratch because you don't want the model to know more than the human you're trying to replicate, right? You want to exactly replicate what the human is. So, yeah, but it's a cool question.
Yeah, this is it's a super interesting question. Um,
Yeah.
awesome. So with that, thank you, Maurice, for the deep dive into the Red Pajama data sets. This is really awesome. Um, any other thoughts or comments before we end it off here?
No, yeah. Also, thanks a lot for all the questions and the engagement. This is really nice to see that people are interested in this and use this. So thanks a lot as well.
Yeah, no, this is awesome. So much engagement, and I'm planning on doing a lot more of these. Is inviting more researchers from the Together team and then outside the Together team to talk about what they're working on, and just to educate the developer community about what it is like to build these language models. And people have really good questions on this, and a
Hmm.
lot of people enjoyed this. So thank you for joining us, and I'll see you around. Thanks, everybody. Thanks, everybody, for
Yeah.
joining. Thanks for the great questions. Take care. Bye.
Thanks. Thanks, everyone.